As measurements are, you might imagine, a rather important idea in the context of physics, we want to spend a little time talking about a way of thinking about what a measurement is, what it represents. So we have this expression that might look a little bit weird at first. Capital X is equal to lowercase x plus or minus sigma sub x. So the capital X represents the true value, but unfortunately that remains unknown. What we can do is make a measurement. We represent that with the lowercase x. But whenever we make a measurement, not only does that not give you the true value, it doesn't give you the true value, possibly because you can only measure a finite number of digits. If I have some digital display for a scale and I want to measure the mass of an object, there's only so many decimal points that I'm able to read off. If I measure something with a ruler, the ruler has divisions that are only so finely placed. Okay, so I can only measure to some degree, and there's going to be a remaining uncertainty that is left. And the way we think about what this is telling us is that the true value is the measured value and then this cloud of uncertainty about the measured value. And the smaller the sigma sub x is, the uncertainty in our measured value of x, then the closer our measured value should represent the true value. Okay. A way to recast this expression that might be a little bit more sensible is to say that the true value, capital X, is bounded. It is going to be bigger than the measured value minus the uncertainty, probably, and smaller than the measured value plus the uncertainty. So this expression that X is equal to X plus or minus uncertainty in X is actually telling us that the true value is bounded by our measurements. And just say a little bit more about this relationship. There are two terms that are often confused as regards measurements. There's the idea of precision, and precision is going to relate to what tool it is you're using to make the measurement. If I do repeated independent measurements, it will be precise measurements if those measurements are all close to one another. That's saying that sigma x is small. Okay. There's another issue, which is accuracy. There could be some bias, some error in our measurement process that is going to cause the true value x to be systematically different than our measured value, lowercase x. And if we want to assess accuracy, then we need to have, by some means, like some other measurement, some other technique, or some inference, what the true value should be. So in accuracy, when we talk about accuracy, if I have an accurate measurement that is telling me that the measured value is close to the true value. So short version, measurements that are precise, the measurements are clustered close together, they're close to one another. If I have additional information about what the true value is, then I can also talk about accuracy. And an accurate measurement will be a measurement that is close to the true value. All right, when we make measurements in this class, we are going to use the metric system, the international system. That is what is used by the vast majority of the world, and even the holdouts in the United States and the UK that don't entirely use the international system. Everything basically is in the international system, but print labels on it to make it think that you're still using gallons or degrees Fahrenheit or measuring things in miles and inches and God knows what else. We are going to be using the metric system because that is the system that is used in science. That is a system that is used by most all human beings. And that is the system that is rational. There's no reason why you should go through your life remembering 5,280 as an important number as opposed to 5,279. In the metric system, everything is base 10, and things tend to have nice round numbers. The density of water, 1 gram per cubic centimeter. The distance from the equator to the pole is 10,000 kilometers. We have nice round numbers in the metric system because it was put together not based on arbitrary things like how long a particular person's foot was, but by things in our everyday environment that would make sense. All right. Going beyond using the metric system, we're going to use a system of units called MKS. So we will measure length in meters, we will measure mass in kilograms, and time in seconds. There are other choices for that, but we are going to use the MKS system. So if you have a doubt about what unit your answer or your values should be measured in, it should be in MKS. And I will likely be marking lots of papers with MKS over the course of the class. For other things beyond length and mass and time, temperature is going to be measured in Kelvin, and a degree Kelvin is the same size as a degree Celsius, but there is no negative temperature in Kelvin. It's set to absolute 0, which is convenient mathematically. And we're going to count the number of particles in terms of Avogadro's number, so a mole of particles. Those are the ones that we're going to need for the P221. Before I run off from this, I will mention that we do still use the sexagesimal system for time. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. So that is handed down to us going back to ancient Babylon. And anytime people have tried to change our measurements of time, like perhaps a base 10 system, those usually fail miserably. People are able to shift how we think about distance or shift how we think about stuff, how much mass there is. We have a very hard time shifting the way we think about time. Have not done that yet. All right. We will sometimes use prefixes to go before our unit of measurement. And most of these are nice Latin letters. And I want to emphasize that capitalization matters. I cannot just drop in a lowercase m when I meant a 10 to the 6, a million as a capital M, because lowercase m already means something. It's already a meter. And I can't drop in a little g when I meant a big G, as little g is already something. All right, so when we're using these prefixes, we're talking like gigapascals, or we're talking about micrometers, then we use these prefixes to have that power of 10. And the ones that are highlighted in a darker font are the ones that we're going to use more so in this class than others. And in fact, in our base unit, we're already into kilo for kilograms. But if you're not familiar with these, you can hop back to this table and have that as a reference.